To see this type of motion in slow motion, it's pretty impressive when you think about it. Setting up cue balls, playing the game of pool, this is a great way for us to talk about not only motion, you guys have heard the word kinetic before, not only the word potential, what could happen with that stored energy, but we also see the cause and effect, that domino effect. Hi, Longhorns. We're going to talk about the conservation of momentum. What happens when one action takes place that equates another action? Because in the end, it all has to be conserved. We are in chapter 6, pages 199 through 203. We're looking at the law of conservation of momentum. There are a couple of key terms I want us to always keep in mind. This whole series, we've been focusing on the word momentum. It's represented by the variable P. We've also talked about what happens when force and time are taken into consideration. Force, time, which equal momentum, will make you think of impulse. Today we're going to layer your thinking and talk about something that you guys have heard about before in classes like chemistry and also biology. We're going to talk about the conservation of energy. Things will start and they may stop, but it doesn't mean that that energy in between or the mass in between is going to disappear. For this PowerPoint, there are a couple of problem examples that you can start off with that are really step by step. And I've included 2 of those for you. So don't forget to pause the video and to visit YouTube for another way to kind of look at things. Now, the big idea is momentum is conserved for all collisions as long as external forces don't interfere. In the upcoming lessons, we'll talk about both the inelastic and the elastic collisions. So what happens when objects come together and separate, and also what happens when 2 objects come together, stick together, and then continue in their motion. For the law of conservation of momentum, you have to keep inside that all external forces must be ignored. So whether it is a car crash, whether it's a game of pool, we don't want any other forces changing the direction of what's taking place. We use cue balls and pool, for example, because it's an easy way to show the transfer of energy and also show that transfer for momentum as well. Now, here's your key point, and this is where those conceptual questions on your test and your quizzes will come from. The momentum of the pool ball after the collision must be equal to the momentum of the cue ball before the collision. So stop and ask yourself this question. What does the word conservation mean? Whatever I start with, I end with. So as we're reading through our different answer choices, keep in mind, if it's conservation of momentum, whatever you start with is the exact same thing that you end with as well. Now, study the following picture. Here I have a cannon that has been loaded with a cannonball. And this dotted line is going to show you the starting point. Suddenly, we're going to pull so that the cannonball can be fired. And if you notice here, there appears to have been some motion. Well, you know that the cannonball went forward or to the right. But for every action, there is an equal yet opposite reaction. If the cannonball goes forward, it's also going to apply enough of that force to force my cannon to go in the opposite direction. Which of Newton's laws states for every action, there's an equal yet opposite reaction? You've got it. So we're looking at Newton's third law. We are taking into account force, mass, and acceleration, which are Newton's second law. Now, here's your reminder, because none of this ever goes away. But when we think about it, here's a key question that you may see. Why is the momentum of the cannonball system equal to 0 before and after the firing? Don't let the wording throw you off. Did you start with a cannon? The answer is yes. Was it loaded with a cannonball? Yes. When we look at these two together, they both create a system. All right, so a system is two objects that are interacting with each other in a particular scenario or story. Why would the momentum of the cannonball system be equal to 0? Because the cannon was initially at rest. If my velocity is 0, no matter what the mass of your cannon is, your momentum will be 0. If I start with 0, whatever I start with is exactly what I am passing on. So before and after would be equal. The other thing they want you to keep in mind is to pay attention to direction. Why is direction important when we're talking about velocity? And it's because velocity is a vector. It gives you magnitude, how much, how big of something you have. But it also tells you direction. In order to get the correct answer for those multiple choice quizzes and tests, I want you to pay attention. If the velocity of the cannon is to the left, then it will always be negative. If the velocity of the cannonball to the right will always be positive. We talked about these directional terms as well when we did scientific notation. Now, before we go, be sure to take a look at a few sample problems. After this, I will have a video where I'm simply working out different sample problems and using the guess method to walk you through. Conservation of momentum is a great chance for us to do that. Many of your problems will have you calculate for the final velocity of an object because you realize that the mass of these objects will not change. I'll see you guys in class.